All right, welcome everybody to lecture 22. So I'll go ahead and share my screen here. So we're starting a new unit. So we just did 4 lectures on star trackers and how star trackers work. And whenever we pivot what unit we're working on, I like to refer us back to this course map, this brilliantly designed and illustrated map that I put together before the first class. This is to give us an idea of everything that we're learning in this course all in one picture. So orbital mechanics was the first several lectures, kind of laying the groundwork for the rest of the work we'd be doing. We then spent some time on estimation theory, illustrated here as an abacus because of math, and that's underneath all of the turtles because math is the basis of everything else that we do. As we started to kind of branch out, we looked at triangulation and trilateration, different methods of navigating with Earth to space and space to Earth measurements. We had 1 lecture on inertial navigation, which didn't show up on any homework assignments. That was kind of just a one-off. And then we had spring break, and we came back with a 4 lecture unit on star trackers, which is the kind of orange box that we see in the diagram here. So that's using a camera and using stars to get your attitude. The next unit is Kalman filtering, which is this little robot looking guy here. So this is not meant to be a cube robot head with a weird looking face. This is meant to be my PowerPoint art depiction of the Apollo guidance computer. And I'm not exactly sure how clearly that came across. But if you look up a picture of the Apollo guidance computer, it's got like, a little 7 segment display and it's got little kind of keys. It's like they had this idea for the Apollo guidance computer to build a board with keys in it. They called it a keyboard. And that was like a new thing at the time. Actually, it was the display and keyboard. So it was the disk key was the whole area here. But it looked a little bit like a microwave. Like it actually had buttons and a little 7 segment display that you could get numbers out of. But this was pretty much the first computer that actually did that. And then there's an area on the top left with different LEDs that could turn on to let you know you were in different phases of flight or different kind of mission statuses. And so the question then is, well, what exactly is running in the Apollo guidance computer, or what exactly is running on any flight computer? So we alluded to this many lectures ago when we were learning about estimation theory, and we talked about if you have many different measurements over time, we can use batch estimation to kind of estimate, use all this information and fold it all into one giant problem where we can estimate the full state or a partial state of the spacecraft at a particular moment in time in one great big batch. And then we alluded to there's also something called sequential estimation. And sequential estimation is if you have a computer running all the time that is constantly keeping track of where it thinks the spacecraft is and is constantly handling new measurements as they come in, that is a sequential estimator. And the most popular type of sequential estimator nowadays is called a Kalman filter. And that is so complicated that it deserves its own unit. So we're going to have a 4 lecture unit on Kalman filters starting today. And then finally, our last unit, which will be as many lectures as we have time for, is images of the Earth and the Moon for navigation. That's called optical navigation or OpNav. And so we'll get there. But first, we're going to focus on Kalman filtering. So that's where we are. It's going to be 2 lectures on the Kalman filter derivation. This is going to be one one kind of grand final boss of a derivation. Going to be a lot of math. Definitely going to be a math intensive unit. Followed by a lecture on kind of practical considerations for the Kalman filter. And then the fourth one is going to be on something called an extended Kalman filter, which is a Kalman filter that can be used for a nonlinear dynamic or nonlinear measurement model, which we have nonlinear dynamics and measurement models. So you will actually need an extended Kalman filter for homework 5. So I kind of alluded to this, but I want to be very explicit. This will be the most mathematically challenging unit. This is definitely going to be a lot, even if you're somebody who's been pretty comfortable in this class so far. If you felt like you were drowning at parts of this class so far, this is going to be worse. So please, like, interrupt me if you're lost. If you're just kind of like, what the heck are we talking about? I guess have a little bit of faith that things will start to make sense at some point. And then B, if I'm just talking crazy, then interrupt me and let me know because there's going to be quite a bit. So the kind of like thought experiment that I want to start us off with is imagine you're going on a road trip. Actually, this might be kind of topical because maybe you're going on a road trip to go see the solar eclipse coming up in a couple of weeks. Let's say that you're driving, just going to make something up, from Troy to Rochester, because Rochester is one of the cities that is going to be, I think, in the path of no totality. So if you're driving from Troy, New York to Rochester, New York, and you have your friends in the car, let's say you're the driver and your friend is the designated navigator because your friend is taking this course, and it's like, oh, well, then they must be a good navigator. So after you've been driving for about an hour, so just thinking, if you're leaving Troy and you're driving about an hour, you might be in the vicinity of Amsterdam, probably not Utica just yet, but you're kind of heading out in that direction, right? And your friend says, "Hey, we're just about to pass Syracuse." And those of you that don't necessarily have the most, I'll do a little map here just for anybody that didn't grow up in New York. So New York kind of looks like this, and then that, and then it does one of these, and then you've got Long Island, right? There you go. And so if you're leaving from Troy, New York, which is roughly here, and you're going to Rochester, which is roughly here, and let's say like this is the path of totality or something like that, right? And let's say you're driving for an hour and you know that you should be roughly here, and your friend says, "Oh, we're just about to Syracuse," and that's, well, you know that Syracuse is right about there, and you're left with a couple of options, right? There's absolutely no way that you drove that far in an hour. It would have had to have been going 200 miles an hour. There's no way, right? So, do you trust your friend in the passenger seat who's supposed to be a good navigator, or do you trust your gut? And your gut says, "I think you're wrong." And then, like, let's go exactly into why do you think your friend is wrong? Well, you think your friend is wrong because you have a mental map of New York State and an idea of how long it's going to take to get somewhere, which means that you have a guess of your current state at any given moment. And maybe you don't put a lot of stock in your guess. Maybe you're not, you don't have a great sense of direction, but you've got a decent idea of how far you can drive. If you're doing 70 miles an hour and you've been driving for an hour, you probably drove 70 miles, not 300 miles or whatever the distance is from Troy to Syracuse. So you're left with, do I trust my mental model or do I trust the observation that just came in? And if you are asking yourself that question, you are a Kalman filter because that is what Kalman filters do. So Kalman filters it's an algorithm that is doing two things. It is propagating a dynamic model that's saying, well, look, I was here and I know the physics and I know the length of time. I should probably be here. That's your propagation. And then it's also updating and it's choosing whether or not it trusts each new measurement as it comes in. If it only trusts the measurement and it ignores its mental model, that's not a Kalman filter. That's saying, okay, friend who has a phone that I don't trust, whatever you say, we're just going to go with that. That's not a very good navigator. However, if you completely ignore your friend and go, no, no, I know exactly what I'm doing, then you've become smug, which is actually the technical term for a Kalman filter, which is rejecting measurements. And so that's kind of our idea of what is, you didn't need to take down the map of New York State. But so that's the motivation behind Kalman filters. So Kalman filters, with each next measurement that comes in, they're comparing what the measurement suggests with what a dynamic model would predict and having to make a decision about how much do we trust A, how much do we trust B. And it's not binary. It's not I trust my model, it's I trust the measurement. It is like a slider, and that slider is constantly moving according to something called the Kalman gain, which we won't get to until next lecture. But hopefully that gives you an idea of roughly what a Kalman filter is and what a Kalman filter does. So speaking technically, unfortunately, I don't have a cool picture to start off with today, but a Kalman filter is an optimal state space model-based estimator. And so you can think of it this way. Kalman filters find the balance between instinct and observation. And by observation, you could think of this as external navigation measurements. And by instinct, what I mean is some sort of internal physics model. So it's going to be important to come back to this because in the next couple of lectures, we're going to get lost in some math. And it's like, okay, well, what exactly are we doing? Oh, we're in the propagate step. That's the instinct step. Okay, great. So that just kind of gives you a nice map of what we're trying to accomplish here. So Kalman filters were introduced by who else? Rudolf, is that PH or F? That's F. Rudolf Kalman in the 1960s and was popularized by its use in the Apollo program. So Rudolf Kalman, when he wasn't busy saving Christmas with Santa, was also working on a optimal navigation estimation tool. So it consists of two main steps. So the first is propagate. That's that physics model step, right? So this is, you could think of it as the natural evolution of the state due to a physics model. And then there's update. And this is a sudden change of the state, accounting for new information. So if things are going well, then when you're discussing your state of your road trip with your navigator, you're not shocked by what they tell you. You might be saying, gosh, okay, I think we've been driving for about an hour and a half. We ought to be coming up on Utica pretty soon. And then your friend says, hey, we're 15 miles outside of Utica. You go, okay, yep, that sounds right. So that's kind of how things go in a perfect world. So you've got your mental model, and then you confirm it with your outside results and your confidence sharply increases. So in a minute, we're going to see a diagram of covariance kind of propagating over time. What you'll see is that your covariance grows slowly as you continue your adventure. You become less and less sure of where you are. And then it very sharply shrinks in size when you go, oh, I am 15 miles outside of Utica. Okay, great. And so it creates this kind of sawtooth pattern, if you will. So a classic Kalman filter, which we'll be talking about for the next two lectures, a classic Kalman filter assumes a linear dynamics model and a linear measurement model. So you might be saying, but Paul, aren't most things nonlinear? It's like, yep, but one thing at a time. We're going to talk about the linear Kalman filter, and then we're going to talk about the nonlinear or the extended Kalman filter in a couple of lectures. The extended Kalman filter is what you'll need for homework 5. So our dynamics model is going to look a little bit like this. So we've got some state x dot is some f of t x of t plus g of t omega of t. Okay? So what do I mean here? the state, the derivative of the state is some matrix times the state, and those things might not be constant in time, right? But this is a linear system, plus G times omega. Well, omega is noise, and then G describes the relationship between that noise on the state and the propagation of the state, essentially. And our measurement model is going to look a little bit familiar. So Y with a little tilde over the top because we know it's noisy is Hx of t plus nu of t. There we go. So this should look similar. So we've seen this linear measurement model. Our measurement y is equal to h, which is some matrix, times x. H should be time invariant. Now, for those of you that are familiar with state space from a controls course, you might have seen x dot is equal to ax plus bu, and then y is equal to cx plus du. This is similar, but this is not exactly that, right? Because this is u is control input. There's no control input here. And we are actually accounting for noise. So there's like some other term, which is the noise term. Similarly, y equals cx plus du, again, where there's no control input, but the x dot equals ax, y equals cx, and then there's some noise, and then there's some noise. That's basically what we're seeing here. So it's not exactly the same as your classic state space, but this should not feel too foreign to somebody who's studied controls before. So let me define some terms here. So in this case, x is the state vector. Y with the tilde is a noisy measurement vector. Okay. Omega is zero mean white process noise. Okay, what do I mean by that? Well, one more thing, and then we'll start talking about what I mean. We've actually seen nu before. Nu is zero mean white measurement noise. So hopefully nu feels like an old friend, right? This is measurement noise. This is, well, we know that y should be h times x, but really there's going to be some noise in our measurements. Nu is the noise in our measurements. Omega is the noise in our physics, right? So that is process noise. So we're going to discuss more on these right now. Okay. So we're going to do a quick aside on noise. Okay. So white noise, you might think of like a white noise machine if you're trying to go to sleep. White noise is a stationary stochastic process. That's the technical term for it. Okay, so what does that mean? So stochastic means it evolves randomly over time. And stationary means the probability distribution is invariant to time. So the probability distribution is invariant to time. So you could think of it as it's a process where, let's say there's some Gaussian, probability distribution function. It's not a changing and evolving probability distribution function. It's random, but the way in which it is random is static, if that makes sense. That's a stationary stochastic process. So the thing about white noise is, no matter how fast we sample white noise, it is truly random. So if you had some white noise and you wanted to find its value, and then you wanted to find its value 1 nanosecond later, a real computer could not do that, right? A real computer, if it was trying to generate random numbers, would actually have some sort of, there would actually be some correlation, and real life random processes don't really work that way either. So if something's random, then if you were to kind of observe it again, a very, very infinitesimally short period of time later, it would be correlated with its previous self because it can't change that quickly. So in real life, there's no such thing as true white noise, but this is kind of one of those it's good enough for us engineers situations. So this is a model. Remember, all models are wrong, some models are useful. So white noise does not exist in practice, but it is a useful mathematical construct. Okay, so pardon me while I go to the next page of my notes here. In our dynamic model, which looks like this, x of t is equal to f of t, x of t plus g of t omega of t. The g of t omega of t term describes the noise that corrupts the dynamics. And so we call this process noise. So we're used to measurement noise, which affects our measurements. This is process noise, which affects our physics model, essentially. And so I have a little diagram here to kind of discuss I'm going to give you a minute to catch up on your notes here, but I have a diagram coming up, which is going to be rather daring for me with my current level of artistic talent. But I want to kind of show a spacecraft kind of moving through space and having constantly changing amounts of certainty or uncertainty based on process noise and measurement noise. So I'm going to scroll down here and start a diagram. So here comes a picture of the Orion spacecraft, of course, including the European Service Module. Say it does that. And then you've got those 4 solar array wings. Good enough. And I'm going to draw 3 of them. And it's got 4 solar array wings. All right, maybe not terrible. And so you can imagine that you've got some physics model, which is predicting where the thing is going to be. And then as you propagate over time, it's like, well, it could be going this way, but we could be wrong. It could also be going this way, and it could also be going this way. So there's kind of some uncertainty here in its propagation. So again, over here, as we propagate, we think it's going to be going some way, but we're not exactly sure. And we're going to have a little bit of kind of drift in our state over time. Now let's assume also that you've got some sort of navigation sensor, which I'm going to show with basically the little Wi-Fi logo here. So this is a nav sensor. And it might be a camera taking a picture of stars, it might be a camera taking a picture of the moon, it might be an antenna that's receiving a signal from Earth, it might be any of a number of things, right? So this navigation sensor. So what I'm showing is at these times that the spacecraft is being drawn, it is actually taking measurements. So we don't really care so much about what happens between the measurements, but when each next measurement comes in, that's when we propagate and update. So at this instant in time, what's really dominating is measurement noise, right? The noise on our signal, whereas in between measurements, it's the process noise that is running the show. And then once again, we have measurement noise. And then once again, we have process noise. And once again, we have measurement noise. Now, if we continue this, imagine that we simultaneously have a graph of our uncertainty over time. Right? So let's say that our uncertainty is drifting and it's getting kind of worse. It's making this like blunderbuss shape. And then all at once, we take a measurement and we go, oh, okay, I think I mostly understand where I am. And then slowly over time, your uncertainty is going to drift and get worse and worse. Here it's happening again. And this is going to be a symmetric graph. So let's say this was the uncertainty in your position on the x-axis. Well, just because you're uncertain, it could be positive or negative, right? So this is typically a symmetric graph or symmetric about some center. And then all of a sudden, you take a measurement and you go, oh, wait a minute. No, okay, I really think I know where I am. Got it. And then this happens again and again and again. So if you look at graphs of the uncertainty that comes out of a Kalman filter, they have a shape that looks kind of like this. So the uncertainty will grow, just like this, get worse and worse. And then all at once, it's never zero, because even when your friend tells you that you're 15 miles outside of Utica, you still don't know if you can trust them necessarily, and 15 miles in what direction, so on and so forth. And this kind of continues. And so you can imagine this continues into the distance, both before and after. And so this is a graph of your uncertainty over time. And if I scroll down a little bit further, this right here is the update step, whereas all of this is the propagate step. And then all at once, we have the update step, and then the propagate step, and then the update step again. So this is the big diagram for Kalman filter. So what I'm trying to get across here is a couple of different things. The relationship between update and propagate, what the uncertainty in your state is going to look like, the relationship between measurement noise and process noise. Notice measurement noise is at the update step, process noise is at the propagate step, and the relationship between when the spacecraft is drifting versus when the spacecraft is taking a measurement. So I'm trying to get a lot of things across in this diagram. So I hope this does a good job of making things make a little bit more sense. And so what we're left with after a few more notes is we're going to talk about how to do the propagation, and that's going to take at least the rest of today. And then we're going to talk about how to do the update, and that's going to take most of next lecture. So we're going to have the propagate step and the update step, and they're both going to be pretty math intensive. Now, there is something called Kalman filter tuning. So the thing is that again, this is a mathematical model, right? And all models are wrong, but some models are useful. You don't know really the measurement noise that's happening. It's like, well, we have a model of our measurement noise. Our model is that, we have 1 nanometer second error on our clock, and that means that we have this range uncertainty or something like that. It's like, sure, but you don't know what's actually happening to your measurement. That is your model, right? So your measurement noise is something that you can kind of tweak and play around with. Although it is, based on a mathematical model, you have kind of a best guess. Similarly, your process noise is also something that you can tweak. So you can adjust these values And what that does is it tunes the confidence of your Kalman filter. You can imagine a really shaky Kalman filter and a really maybe kind of brash and overcompetent Kalman filter, right? So if your process noise as modeled, because real life is real life, it's just going to do what it wants. But if your modeled process noise is too small and your measurement noise is too big, what that means is you tend to want to trust your dynamics a little bit too much, and you might go as far as to ignore your sensor, which leads to something called a smug filter, which is the actual technical term. In this case, this would be when you completely ignore your friend and their best efforts at navigation in the passenger seat. By contrast, if you have the process noise is way too small, sorry, other way. Process noise way too big, and the measurement noise is way too small. We're saying, gosh, I just don't really trust my physics at all. I'm just going to do whatever my friend says. If they say we're outside of Syracuse, then why not? In this case, you would be ignoring your dynamics. And that is just a measurement pass through. It's not a filter at all. We're just going to trust whatever the measurements say, right? So a wise captain kind of discerns between what their gut says and what the navigator says, right? And that's the idea here. So Kalman filtering then is a continuous Goldilocks problem of trying to get everything just right. That's the idea. Okay, so this is a really good time to pause and answer any conceptual questions. So we haven't had that much in the way of math just yet. That is about to change. We're about to basically jump off a mathematical cliff with a thin bungee cord. So before we do that, any questions about what we've discussed so far? All right. Going once, going twice. Sold.
Sorry, I have a
Howdy.
I have a quick question.
Sure.
So you didn't include any control
Yeah.
above. How would we include any sort of control or uncertainty in the control?
Oh boy. Beyond scope is my short answer. So there is definitely the your mathematical model would need to be something like it'd be three terms. So to be like ax plus bu plus c omega, something like that. And then you've got, yeah, exactly. So you've got your control input, but then you've got whatever uncertainty there is. We would probably roll the uncertainty in the physics and the uncertainty in the state propagation and the uncertainty of the effect of the control inputs would probably be rolled all together into process noise. But in this case, just like for this homework assignment, we're looking exclusively at how this state is going to evolve naturally without any control inputs. But that's a very good question. So for a true, like when you're actually going through and putting together your filter for a spacecraft that has control inputs, estimation theory and control theory are next door neighbors for a reason, right? So you would want to count for both of those. We won't in this class, though.
Okay, thank you.
Yeah. No, good question. Absolutely. I'm glad you're thinking along that line. Anybody else? Otherwise, we're on to state and covariance propagation. All right, cool stuff. So we're going to go as far as state propagation, and then we might take a little break. That might be good. So we will begin with our dynamics model. And so that would look like this. X of t, or x dot of t, is f of t, x of t, plus g of t, omega of t. Okay. So this is obviously, for anybody with a brain could tell you, this is a first order stochastic differential equation. Okay, maybe not. Maybe it's not so obvious, but let's look at it for a second. This is a differential equation of the form x dot is equal to ax plus some stuff. That is a first order differential equation, and there's random numbers in there, which makes it stochastic. So this is a first order stochastic differential equation. And for those of you that remember diff EQ, if you have a first order differential equation, you know it has a solution of the form, like there's kind of a cookie cutter template of what your solution is going to look like. And the only thing you need to do is find the coefficients or the parameters within that solution. That might sound a little bit familiar from differential equations, but we'll see in a second. This is going to make a lot more sense. So this is a first order. There we go. Stochastic differential equation with a solution of the form x of t is equal to capital phi t comma t naught x of t naught plus the integral from t naught to t, capital phi t comma epsilon g of epsilon omega of epsilon d epsilon. So this is our solution. Now let's look at it one thing at a time. The very first thing we should notice is this fella. Remember our friend from before, the state transition matrix? It's back, right? So what we're saying here is if we have a differential equation of the form x dot is equal to ax, then we have a solution of the form x is equal to a state transition matrix times its initial condition, right? So essentially, the mathematical relationship between some state and some later state is just a matrix, and that matrix is our friend, the state transition matrix. So the first part is nice and simple. X is phi times x naught, right? All of this is to account for the effects of noise, because what's really happening is at every infinitesimal time step, noise is going to be perturbing things. And so what we really need to be doing is accounting for the perturbation of noise at some infinitesimal time step, but there's infinitely many of those. And when we add up infinitely many infinitesimally small numbers, that is an integral. And this term accounts for the effect of noise. Okay, so maybe this equation looks scary at first, but now we understand what each of the terms mean. Maybe it's not quite so bad. Now I should reintroduce our friend here, where phi of t and t naught is the familiar state transition matrix, which behaves according to, so you might remember, this is old news, right? Phi from t naught to t naught is just the identity matrix, n by n, and phi dot between the initial time and the current time is f of t phi of t and t naught, where f is the same f as in our dynamics model. So the same f that controls the propagation of the state over time controls the propagation of the state transition matrix over time. So neither of these equations is news. We've seen this before. I just wanted to reintroduce it. Okay. Now we make some assumptions. We assume that omega of t is zero mean white noise meaning that the expected value of omega of t is 0. Really, this would be a vector of zeros, right? Because there's omega is a vector. And then the expected value of omega of t multiplied with itself at some other time. This is a crucial difference, right? Omega of t, omega of epsilon. So in this case, epsilon is just some time that is maybe t, but not necessarily t. Well, this is going to be q of t times delta of t minus epsilon. So let's break this down. This is two different things. So you could think of q as our process noise covariance. So we've got our measurement covariance matrix before. We talked about capital R, right? Q is our process noise covariance matrix. And then there's this delta. So what is this delta? Let's make some sense out of that. So in this case, say where t is some time, epsilon is also some time, and delta is what's referred to as the Dirac delta function. Okay, sounds pretty complicated. Bear with me, this is going to get easier. The Dirac delta returns a 1 if the input is 0, returns 0 otherwise. Okay, so how does that help us? So if t minus epsilon is anything, which is to say that if t and epsilon are not the same thing, then this delta is 0 and the covariance between them is 0. That is to say that your noise is completely uncorrelated with itself at any other time. Right? There's no relationship between what the noise is right now and what the noise measurement is a year from now, or between what it is now and what it is 1 nanosecond ago. Is completely uncorrelated. However, if we're comparing it to itself, it does then have some covariance, which we would expect to see, right? So in plain English, we would say, well, I guess this is still math, not English, but omega of t, let's see, omega of t1, omega of t1 transpose, that is going to be q t1. However, the expected value of omega t1, omega t2 transpose is 0. Okay. Therefore, now that we know all this, we can take the expected value of our equation. So we know we're going to have a solution of the form this. So what do we expect the solution to be? So let's do that. The expected value of x of t is, and we're going to use the notation x with a hat. This is going to be a bit confusing. In the star tracker unit, the hat means a unit vector. In the Kalman filter unit, the hat means it is our estimate. It is our optimal estimate, not the actual thing in itself. Okay. I recognize that can be a bit confusing. There's really so many like letters and things that I can use, so we end up doubling up on notation sometimes. So please just keep it straight in your head that in this unit, the hat means it is our estimate, not necessarily a unit vector. So let's take the expected value operation here. So the expected value of the state is the expected value of the entire right-hand side. So we're going to write it out again. Remember, it's phi t and t naught x of t naught plus the integral from t naught to t phi t and epsilon g epsilon omega epsilon d epsilon. Okay. So remember that the expected value distributes. So the expected value in this case would pass right through the phi because phi is not stochastic in nature. And it's going to cling onto our initial value. And it's also going to cling onto our noise, right? Because there's nothing about G that is stochastic. There's nothing about phi that is stochastic, but there is absolutely something about omega that is stochastic. So we're going to consider that. So let's clean this up a little bit. So that means that the expected value of x of t is equal to phi t and t naught, expected value of x of t naught plus the integral from t naught to t phi of t and epsilon g of epsilon, expected value of omega of epsilon d epsilon. But remember, what is the expected value of our noise? It's 0. So the whole second term goes away. So thankfully, we can say that the expected value of our state at some time t is phi t and t naught times the expected value of our initial state. Right? So if you have some initial state estimate, you can just go ahead, right ahead and propagate it, because the noise, while it does matter, actually this is going to get a red box. While the noise does matter, while the noise is perturbing things, we assume that because it is zero mean and completely random and non-biased, that what's going to end up happening is that the noise will have the ultimate effect of canceling itself out on average, so we're not going to account for it. So when the time comes to propagate your state, you just go right ahead and use the good old-fashioned state transition matrix. So this is the state propagate equation. Now, this works, I want to make it very clear. This works because we assumed white process noise. If your noise was biased, this might be a mistake. If your noise was biased, then the expected value operator here would not be 0, so we need to take that into account. Okay, so the state propagation is done. Next is our covariance propagation. And the covariance propagation is about 4 times as complicated. So that's a good point for a natural stopping point for a break. So it is 6:57 for me. It's really 6:58 probably. Let's say we'll take a break and we'll come back at 7:03. How does that sound? And I'll stick around during the break to answer any burning questions that you might have.
I have a question about the extra credit.
We might discuss that afterwards, unless it's a really burning question. I'd rather keep it to the Kalman filter stuff right now.
Oh,
Can you
okay.
hang out until after class?
Yeah, I can wait.
Okay, perfect. All right, we're going to get this train back on track, and we're going to talk about covariance propagation, which is going to be a little bit more involved. And I think that that might be all that we have time for today. It might be that we reach a natural stopping point after that. And then we pick up next time. Yes. Okay, well, let's get back on track one way or the other. Any other kind of Kalman filter questions that are swirling around in your head, or are we good to keep moving? Unless somebody interrupts, I'm going to start talking about covariance. So we now turn our attention to covariance. So remember the definition of covariance, right? So P of T is the expected value of the state minus the expected value of the state. And then all of this times itself again, state minus expected value of the state, transpose. Okay. Now, it is not at all trivial to show, so I'm going to skip a huge step, that this can be simplified to. It might seem like it's easy, but it's like, well, it takes a little bit more math than you'd think. This can be simplified to the expected value of x of t transpose minus the expected value of x of t times the expected value of x of t transpose. So the thing is, we know this, right? We know expected value of x of t because that's just what we already had. That's the state propagate step. So let's focus here. So the expected value of x of t transpose, well, we're basically going to need to write out what is x of t transpose, and then take the expected value. So we're entering the realm of, gee, I sure hope we can fit this equation all on one line, and we're going to be there for a while. So the expected value of x of t transpose is the expected value of, open parentheses, phi t naught x of t naught plus the integral from t naught to t of phi of t and epsilon, g of epsilon, omega of epsilon, d epsilon. Okay, and then all of that again transposed. So phi t naught x of t naught plus integral t naught to t t and epsilon, g of epsilon, omega of epsilon, d epsilon. All of this transposed. Okay, so what's that going to look like? Well, that's going to be when you transpose this second term, what you're really doing is changing the order, right? So if we transpose A plus B, that's the same as A transpose plus B transpose. But remember, if you have A, B transpose, that's the same as B transpose, A transpose. So if you want to distribute the transpose, you have to change the order. So this equals, oh, switch to pen, there we go. This equals expected value of, this first part is the same. So I would just like copy paste, but you who are writing in pen can't copy paste. And so in solidarity, I will write it a second time. X of t naught plus integral t naught to t phi t epsilon, g of epsilon, omega of epsilon, d epsilon, close. And then this is going to change our order. So all of a sudden, this is going to look like x of t naught transpose, phi of t naught transpose, plus the integral from t naught to t of, let's see here. Oh, you know what? I made a mistake. Okay, my apologies. I want to make this more clear. Over here, this epsilon is not necessarily the same as this epsilon, right? Because it's a different term that we're going to be integrating. So to make this more clear, I'm going to introduce a different value here. So I apologize to everybody who already wrote that in. I'm going to use eta. So I'm going to use eta here, eta here, eta there. Apologies for that. So I want to make it clear that this epsilon and this epsilon are not necessarily the same thing, right? It's the term that is being integrated. So you can use really whatever letter you like, but I'm going to use a different letter just so we don't get ourselves confused. Okay, so now this becomes omega of eta transpose, g of eta transpose, phi from eta to t transpose, and then d eta, right? Because this is a scalar, so it doesn't matter that that goes at the end. Everything else is a vector in there. And then this ends in parentheses and then a bracket. There we go. Just barely all fits on one line. Okay. So next we are going to do two things. So next we distribute terms and the expected value operator. So remember, if you've got A plus B, C plus D, now we're going to be doing AC plus, so first, outer, inner, last, right? AD plus BC plus BD, right? So that we're about to do that. And simultaneously, we're going to kind of move the expected value operator to where it matters, right? So the expected value operator does not care about phi, it does not care about G, it does not care about, well, that's about it. It definitely cares about the state and about the noise. So everything that might have a stochastic element to it. So it's going to look like we're skipping steps here, but thankfully, things are actually about to get a little bit simpler, if you can believe it. So the expected value operator on x of t transpose is equal to, this is where we don't even have a prayer of getting this all on one line. So I'm going to do it on 4 lines. Each term is going to get its own line. So first we have phi times x times phi. And so it's going to look like this. Phi t and t naught. And then we've got the expected value of, because that's going to apply only to the x's, x of t naught transpose times phi of t to t naught transpose. Okay, so far so good. Next is going to be the outer term. So it's going to be phi times x multiplied by this kind of integral here. And so what's going to end up happening is this is going to look like phi t naught to t, begin the integral, t naught to t, then the expected value operator, x of t naught, omega of eta transpose, and then we close the expected value operator because the expected value operator doesn't care about g of eta transpose or phi from eta to t transpose t eta. Right, so, okay. And then we're going to do the same thing. So it's going to be the inner term. So it's going to be, well, we'll see in a second here. It's going to be plus the integral from t naught to t of phi t and eta, g of eta. And now here's where the expected value operator starts to come in. We've got omega of eta, and then we've got x of t naught transpose. Okay. And then we've got phi t to t naught transpose d eta. There's our third term. Oh, sorry, there's no close parentheses. There's our third term. And our fourth term is going to be the integrals multiplied together. And so it's going to be a double integral. So we've got the integral from t naught to t, the integral from t naught to t of, let's see, one thing at a time. So phi t to eta, and then we've got the expected value of, oh, you know what? I have a mistake in my notes. I made a mistake because there should be a g. Apologies. Let me fix that on my paper here. This should have a g of eta, or sorry, g of epsilon. G of epsilon. And then we have the expected value of omega of epsilon, and then omega of eta transpose. Okay. And then we've got g of eta transpose phi of t to eta transpose d epsilon d eta. Okay, this is about to get a lot nicer, so bear with me here. What is the expected value of t naught, or sorry, of x naught transpose? Well, that's just our initial covariance. So that simplifies. What is the expected value of the noise multiplied by the state? Well, those things have nothing to do with one another, right? It's white noise. So this term is 0, so we drop it completely. By that same logic, this term is 0, so we drop it completely. And finally, what is this except for Q, right? This is our process noise covariance matrix, except that eta and epsilon are not necessarily the same thing. We're going to write this as Q epsilon Dirac delta function of epsilon minus eta. Okay, so this is going to get a lot simpler in a hurry. Now, we can actually simplify things even a little bit further here. So let's scroll down a little bit. Two neat properties of the Dirac delta function. Okay. The first is that the integral from negative infinity to infinity delta of t minus tau d tau is 1. So the area under the curve is 1. Secondly, the integral from negative infinity to infinity of some function of tau times the Dirac delta function of t minus tau d tau is just f of t. Why do we care about that? Because we've got a double integral here, and by exploiting this second identity, we can actually turn it into a single integral. So things are going to get a little bit friendlier for us. So therefore, we can greatly simplify. So going back up to this 4-line monstrosity, the first term is pretty simple. The second term goes to 0. The third term goes to 0. And the fourth term turns into a single integral, which is, not great, but it's a little bit better. And so let's see here. I'm going to leave it as this. So the expected value of x of t, x of t transpose is phi of t and t naught. Oh, you know what? I jumped the gun. Hang on. Sorry. This is not p naught. This is it. We're heading in that direction. It's actually one of the terms in p naught, but we're not quite there yet. So that term, we're going to leave it exactly the same. So apologies for that. Expected value of, there it is. Okay, I lost my place. X of t naught, x of t naught transpose phi of t and t naught transpose. So there's our first term. And then our fourth term becomes a single integral from t naught to t of phi t and epsilon g of epsilon q of epsilon, and then we have g of epsilon transpose phi of t and epsilon transpose d epsilon. Okay, so now what we can do is we're going to plug this back in our equation for covariance. Remember that covariance E of t is the expected value of x of t transpose minus the expected value of x of t expected value of x of t transpose. Okay, so now we have the first term. Now the second term is, remember this. So we've got the expected value of x of t is equal to phi t and t naught expected value of x of t naught. Right? So we're going to be plugging in these two terms for the first thing and then this term for the second thing. And so this is going to get busy again in a hurry, but then fortunately things are going to simplify one more time. And so let's see here. Just want to get my place on the notes. Okay, yep, here it is. So P of t, we have a chance of fitting this all on one line. We might be able to, is phi t naught expected value of x of t naught transpose phi of t and t naught transpose plus the integral t naught to t phi of t and epsilon g of epsilon q of epsilon g of epsilon transpose phi of t and epsilon transpose d epsilon. Nope, it's not going to fit. Minus phi of t and t naught expected value of x of t naught expected value of x of t naught transpose phi of t and t. Oh, scooch over a tiny bit. Ooh. Okay, almost fit it. There it is. So there's our Holgorey equation for P of t. You know, I'm just gonna scooch this over a little bit as I can. I know it's cheating because you can't do it, but I'm just trying to fit it all on one line. There we go, or on one width of the screen, I should say. Okay, so now what we can do is combine our first and our last terms. Because if you look at the first term, it's phi times some stuff times phi transpose. And the third term is phi times some stuff times phi transpose. And this integral term is going to stay exactly the way it is. Okay, so if we combine first and last terms, okay, so we're going to get P of t is phi of t and t naught. And then I'm just going to have a big old bracket out here. This is the expected value of x of t naught, x of t naught transpose, and then minus, so this is the third term now, the expected value of x of t naught expected value of x of t naught transpose, and then all of that times phi t and t naught transpose. And then we begin the integral term. So this is plus integral from t naught to t, phi of t and epsilon, g of epsilon, q of epsilon, g of epsilon transpose, phi of epsilon and t transpose, d epsilon. And now this is where we can say all of this is p at t naught, right? So that is exactly the same equation as we have for p of t, except everywhere you would expect to see a t, you see a t naught. So finally, after a bit of math, we arrive at our equation for our covariance as a function of time. And so it looks like this. P of t is phi between t and t naught, p of t naught, phi between t and t naught transpose. So that is kind of the dumb way of doing it. So if we just had this first term, we'd be saying, well, just take the old covariance and use the old state transition matrix on it. Of course, because covariance is a matrix, it needs to be sandwiched between state transition matrices rather than just having one out front. But then we've got this second term, which is the term that basically inflates the covariance and makes it bigger. And this cannot be ignored, right? Because even though uncertainty, we kind of pretend that when we propagate the state, the uncertainty doesn't matter because it should cancel out. As we continue to propagate our state, we should be less and less sure of it over time. And this is the term that accomplishes that. So that is the familiar integral from t naught to t, phi of t and epsilon, g of epsilon, q of epsilon, g of epsilon transpose, phi of t and epsilon transpose, d epsilon. Right? Nice and simple. I mean, compared to the math that we were seeing a second ago. So this is our covariance propagation equation. Yep. There it is. This is covariance propagation. What you'll see with Kalman filters is that just keeping track of the state is one thing, but keeping track of how sure we are about the state is entirely another thing. And that really is where most of the kind of anguish comes from. And so if you'll permit me to summarize and kind of compact my notation a little bit here. So when the time comes to actually update, you're not updating from some initial state. You're updating from, if we scroll up to our spacecraft diagram like this, what you're really doing is you are propagating from some previous state to some next state, not always from the initial state to the current state. And so we really only need to know how to transform between our last state and our next state. So we're going to simplify things a little bit. So in summary and compacting notation, we're going to say that x hat of t at time tk is phi that maps between tk minus 1 and tk. So this is, k is just your index, right? So this could be t2 and t3 or t4 and t5, right? Same idea. And then this is just x at the previous time, tk minus 1. And then following this, your covariance at tk is phi between tk minus 1 and tk, your covariance at tk minus 1, phi between tk minus 1 and tk, transpose, plus the integral between tk minus 1 and tk of phi of tk and epsilon G of epsilon, Q of epsilon, G of epsilon transpose, phi acting between epsilon and TK transpose, d epsilon. And this is where this integral is a lot and it's getting frustrating. So what some people will do is they will just say, let's define this whole thing as being just some QK, which, to be abundantly clear, is not the same thing as Q of epsilon. So using the same letter might be a mistake, but this is kind of the notation that you'll see where, you know, the QK is this whole integral expressed as a single letter, and it's not the same thing as the Q that's in the middle of the integrand, right? We're not dropping everything on the left and right. And so if we define, just to make it even a little bit simpler, if we define phi k as being the phi that gets you to the TK from TK minus 1, then our equations become even simpler. So we just get x at TK is phi k x of TK minus 1, and we get P at TK is phi k P at TK minus 1, phi k transpose plus UK. So this is kind of the compact form of what we're used to seeing. So this is both of the equations that we learned today, state and covariance propagation, but this is just over one little time step. There we go. And even though there's much, much more to talk about, I feel like that's probably plenty for one day. That's pretty dense. There is actually a simpler way to do state and covariance propagation. And I mean, not much simpler. It's about a page and a half of dense math as compared to 2.5 pages of dense math, which that just was. However, there are some issues when you use the simpler method that you're kind of inviting trouble into your Kalman filter when you use the simpler method. So I'll teach it to you for your awareness, and then we're going to shift focus to the measurement update step, which is going to be kind of the rest of our time. So questions on Kalman filters? Otherwise, we will wrap up and dismiss for the day. And once again, just want to reiterate, I know this is a lot. This is gonna, things are gonna click into place in about 2 lectures from now. So just kind of have some faith and take the best notes you can, and things are gonna hopefully click in a little bit. But if there aren't any questions, then we will dismiss for the day. So thanks everybody for coming. I'm going to stick around if you have any homework or other specific questions. I'll be here for at least another half hour. So yeah, thanks everybody, and have a good rest of your day.